Welcome back to Module 1, Unit 2, Lesson 4 in our study of the fundamentals of operating systems. This course is based on the text Operating System Concepts by Abraham Silberschatz, Greg Gagne, and Peter B. Galvin. Make sure you have your study guide handy so that you can make a few notes. We're going to pick up where we left off by exploring in more detail the various types of system calls from the 6 major categories of process control, file management, device management, information maintenance, communication, and protection. So let's get started. A running program needs to be able to halt its execution either normally or abnormally. If a system call is made to terminate the currently running program abnormally, or if the program runs into a problem and causes an error trap, you remember our discussion of traps, a dump of memory is sometimes taken and an error message is generated. The dump is written to a special log file on the disk and may be examined by a debugger, which is a system program designed to aid the programmer in finding and correcting errors or bugs to determine the cause of the problem. Under either normal or abnormal circumstances, the operating system must transfer control to the invoking command interpreter. In an interactive system, the command interpreter simply continues with the next command. It is assumed that the user will issue an appropriate command to respond to any error. In a GUI, a pop-up window may alert the user to the error and ask for guidance. Some systems may allow a special recovery action in case an error occurs. If the program discovers an error in its input and terminates abnormally, it may also define an error level. More severe errors can be indicated by a higher level error parameter. It is then possible to combine normal and abnormal termination by defining a normal termination as an error at level 0. The command interpreter or the following program can use this error level to determine the next action automatically. A process executing one program may load and execute another program. This feature allows the command interpreter to execute a program as directed by, for example, a user command or a click of a mouse. Where is the control to be returned when the loaded program terminates? This question is related to whether the existing program is lost, saved, or allowed to continue execution concurrently with the new program. If the control is returned to the existing program when the new program terminates, we must save the memory image of the existing program. So we have effectively created a mechanism for one program to call another program. If both programs continue concurrently, we've created a new process to be multi-programmed. Often there is a system call specifically for this purpose, create process. Now let's examine several common system calls dealing with files. We first need to be able to create and delete files. Either system call requires the name of the file and perhaps some of the file's attributes. Once the file is created, we need to open it and use it. We may also read, write, or reposition. Reposition means to rewind or skip to the end of the file. Finally, we need to close the file, indicating that we're no longer using it. We may need these same sets of operations for directories if we have a directory structure for organizing files in the system. Believe it or not, a directory is normally just a file that displays the name and other information about other files that have been assigned to that directory. It's not like the operating system organizes the files physically on a storage device. We'll find when we study the secondary storage that the operating system actually puts a file wherever it can find a space, and may in fact have a file scattered all over the storage device. In addition, for either files or directories, we need to be able to determine the value of various attributes and possibly set them. File attributes include the file name, file type, protection codes, accounting information, and so on. At least two system calls, get file and set file, are required for this function. Some operating systems provide many more calls, such as calls for file move and copy. Others might provide an API that performs those operations using code and other system calls. And others might provide system programs to perform the tasks. If the system programs are callable by other programs, then each can be considered an API by other system programs. A process may need several resources to execute: main memory, disk drives, access to files, and so on. If the resources are available, they can be granted, and control can be returned to the user process. Otherwise, the process will have to wait until sufficient resources are available. The various resources controlled by the operating system can be thought of as devices. Some of these devices are physical devices like a disk drive, while others can be thought of as abstract or virtual devices such as files. It may come as a surprise to us that a file is not really a physical entity. Rather, it's a collection of data that is viewed as a unit, which gives that abstract view of a file. A system with multiple users may require a process to first request a device to ensure exclusive use of it. After it's finished with a device, the operating system must release it for the process. These functions are similar to open and close system calls for files. Other operating systems allow unmanaged access to devices. The hazard then is the potential for device contention or perhaps deadlock. Once the device has been requested and allocated to the process, we can read, write, and possibly reposition the device just as we can with files. In fact, the similarity between input-output devices and files is so great that many operating systems, including Unix, merge the two into a combined file/device structure. In this case, a set of system calls is used on both files and devices. Sometimes input-output devices are identified by special file names, directory placement, or file attributes. The user interface can also make files and devices appear to be similar, even though the underlying system calls are not. Many system calls exist simply for transferring information between the user and the operating system. For example, most systems have a system call to return the current time and date. Other system calls may return information about the system, such as the version number of the operating system, the amount of free memory space or disk space, and so on. Another set of system calls is helpful in debugging a program. Some systems provide calls to dump memory. This provision is useful for debugging. The program strace, which is available on Linux system, lists each system call as it is executed. Even microprocessors provide a CPU mode known as single step, in which a trap is executed by the CPU after every instruction. The trap is usually caught by a debugger. Many operating systems provide a time profile of a program to indicate the amount of time that the program executes at a particular location or set of locations. A time profile requires either tracing facility or regular timer interrupts. At every occurrence of the timer interrupt, the value of the program counter is recorded. With sufficiently frequent timer interrupts, a statistical picture of this time spent on various parts of the program can be obtained. In addition, the operating system keeps information about all its processes, and system calls are used to access this information. Generally, system calls are used to get and set process information. There are two common models of inter-process communication: the message passing model and the shared memory model. In the message passing model, the communicating processes exchange messages with one another to transfer information. Messages can be exchanged between the processes either directly or indirectly through a common mailbox. Before the communication can take place, a connection must be opened. The name of the other communicator must be known, be it another process on the same system or a process on another computer connected by a communication network. You'll learn about network communication in your networking or distributed systems course. In the shared memory model, processes use system calls to create and gain access to regions of memory owned by other processes. Remember, normally, the operating system tries to prevent one process from accessing another process's memory. Shared memory requires that two or more processes agree to remove this restriction. They then exchange information by reading and writing data in the shared areas. Once the memory has been shared, the form of the data is determined by the processes and is not under the operating system's control. The processes are responsible for ensuring that they are not writing to the same location simultaneously. Later, we'll look at a variation of the process scheme, threads, in which some memory is shared by default. Both models, just discussed, are common in operating systems, and most systems implement both. Message passing is useful for exchanging smaller amounts of data because no conflicts need be avoided. It's also easier to implement than shared memory for intercomputer communication. Shared memory, on the other hand, allows maximum speed and convenience of communication since it can be done at memory transfer speeds when it takes place within a computer. I'm guessing, test-wise, that it might be a good idea to remember the difference. Problems exist, however, in areas of protection and synchronization between the processes sharing memory. Protection provides a mechanism for control and access to the resources provided by a computer system. Historically, protection was a concern only on multi-programmed computer systems with several users. However, with the advent of networking and the internet, all computer systems, from servers to mobile handheld devices, must be concerned with protection. Typically, system calls providing protection include set permission and get permission, which manipulate the permission settings of resources such as files and disks. The allow user and deny user system calls specify whether particular users can or cannot be allowed to access certain resources. Here are some examples of some Windows and Unix system calls. Feel free to pause the video and look them over. That concludes our investigation of the 6 types of system calls that are found in an operating system. Let's take a break here before we start the next section. Look over your notes, take care of any business you need to take care of, and whenever you're ready, come on back and we'll start Lesson 5 of Unit 2 of Module 1.